you can sleep, but which is not true. Because from tomorrow regarding the physics, we will move to special things like electromagnetic physics description in Geant4 and then the available processes, models, and so on. After tomorrow, it will be the same in hadronic physics. But before that, there are some special, sometimes also exotic physics in Geant4 that are sometimes, like as you can see here, they are a bit out of the mainstream simulation. But it's good to see that there are applications and there are extensions in Geant4 that makes possible to simulate even this kind of things. You will see, I will mention that for example, these kind of things are really special if we are talking about particle transport simulation. So these things are decay. A bit I will talk about this. Makoto already mentioned the decay table a few times. Now he will see what is this decay table, actually how decay is handled in Geant4, how you can change this decay and so on. Then the special things, the low energy photon interactions, the optical photon interactions. I will mention why they are different and what interactions are there. Now, even with optical photons, already you will see that it's the material description that you see today is not enough to do optical photon interactions. You, as a user, if you want to use them, you need to provide some extra information regarding your material properties to do this. It's more true for these interactions like phonon, electron hole propagation, or channeling, because you need to provide crystal structure information. I will say more when we get there. So regarding the decay, as Makoto already mentioned, you might see something also on this on Thursday. But as Makoto mentioned, for all unstable long-lived particles, Geant4 provides decay channels, decay table, in the form of decay table. You will see what is it later on. I already mentioned before lunch that decay can happen in flight when the particle is still moving. At a point can decay, even if its kinetic energy is still non-zero. Or when this particle will stop and can decay, then sooner or later it will decay. So it's a discrete at-rest process, actually the decay process. And it's a bit different than the usual interactions, because in case of Bremsstrahlung, what you saw before lunch, that there is a differential cross-section. So if differential in whatever, okay, it can be differential actually. Usually when you start, it's differential in many things. Then if you integrate everything, you get the integrated cross-section, the atomic cross-sections. This describes the rate of interactions, in that case, Bremsstrahlung photon emission, in case of one atom. But in a material, you have many atoms. So when the photon is moving in a material, then it will see not only one atom, but there will be some atom density. Okay. So if you multiply this atomic cross-section by the number of atoms per unit volume, which is the atomic number density, you will get the so-called macroscopic cross-section. That describes the rate of happening of that interaction in the material already, not in atom. And the inverse of this macroscopic cross-section is called the mean free path. Why it is called there, you will see tomorrow. And this is the usual way in which physics processes determines the mean length that the particle travels between two interactions. Okay. But in case of decay, the story is a bit different, because we have the lifetime. So the mean length traveled till the decay will be determined in a slightly different way. Okay. When the particle is still moving and when the particle stops, actually when the decay happens, it will be determined by time, not the length. Okay, I think it's understandable. Most of the time, it's actually not important this time. Why? Because there is nothing else that can happen with the particle except when it stops, that after a while it will decay. So when the time comes, it will decay. Okay, because there is nothing. But in some cases, like I mentioned muon, when the muon stops, it can form muonic atoms, and either the muon will decay or will be captured. So there are actually two interactions competing, and they will competing not in length, what I told you before, because the muon is stopped, doesn't move, there is no length. They are competing in time. The one will be the winner that will give the shortest time. Okay, and shortest means not in average, but based on the mean time, there will be some random sampling. So sometimes, if a muon stops, it will be decay. Sometimes it will be captured. And the probability is determined by the ratio of these mean times. Okay. So you also saw this point actually yesterday when I showed an example in the physics list how to add the decay to particles. I told you that decay process can be assigned to many particles, few hundred particles. So you saw that decay process actually knows if it can be assigned to the given particle. So we just go through the particle list, and whenever we can assign, we assign exactly the same process. Now, different particles will have different decay modes, decay channels, but all the decays can be described by one process. This is because the different decay channels that are particle specific are stored not in the process, but in the particle. They are stored in a particle in a form of a decay table, not directly in the particle, but through the particle, somehow attached. Okay, it's not so important. But before we go to the decay table, just a few things that, regarding decay, there can be 2, 3, and many-body decay. You can see an example for the two-body decay. This is the electromagnetic component of a hadronic shower, actually pi 0 to 2 gamma. Or it's also possible, and you can see that it's when a pi 0 will decay, I already wrote that actually 98.9% this will happen. But not always. There are other possibilities, but with a lower probability. And actually also, one of these gamma can already produce a lepton pair. As you can see here, this is the same things, but one of the gamma is already producing a lepton pair. All the double dalits also exist when the second gamma is already producing also lepton pairs. Now, regarding muons, I will get back to muon minus and muon plus decay because there are some special decay processes for this. But what I wanted to say, and probably the most important thing, as Makoto mentioned, that each particle who has decay, there is a decay table. Okay, a decay table is nothing. It's not rocket science, as you can see. You can imagine that each line contains the possible decay products. Okay, as you can see, and each channel has some percentage. So when a particle, in this case, if you sum them up, you need to get one probability. In this case, in percentage, 100%. If you sum these up, you will get almost 100. So it's not all the possibilities. I didn't list everything. I listed some examples for leptonic, semi-leptonic, hadronic decay channels, and so on. But what happens when K1 plus reach the point where it needs to decay? Then actually decay process will come to this table. Based on these discrete probabilities, we select now sample 1 channel. This will be taken by 63%, 0.634 probability. This one with a significantly lower probability, and so on. And then the K1 plus will decay into this decay product. Okay, so it's very simple. So this is why it's very simple to change this. If you want to change, you can come and you change this. Or you derive another one and attach to the particle another one. So this is what I'm saying is that you can redefine these decay channels easily. If you go to the code, you will see like this, actually, in this table. Not in this nice table format, of course, in a code, but kind of this format. For short-lived particles, there are no things like this. So if you want, you need to provide actually by yourself everything, or as was already mentioned, you can even call some external generator for decays. So when I was showing muons, I mentioned that there is a special things G4 decay with spin. It's like if you initially assign the spin to a muon, then it will be tracked during the transport. And when that muon decay happens, actually what I was showing, then it can be done in such a way that the spin is taken into account. And this special decay process handles this kind of things. Or another special decay process that is nicely called unknown decay, because this is still not yet discovered particles. So actually, of course, we don't know anything about how they will decay. But if you want, you tell in the form of decay table, and they will decay if time comes. Now, let's move from decay to the optical photon processes. And first of all, what we need to see clearly is that these are photons. These are gamma photons. Okay, the difference when we are talking about optical photons and gamma particles is the energy range. Here we are talking about very low energy photons. Very low is not well defined. What is more well defined is that their wavelength is much longer than the atomic spacing. Okay, so whatever they do, you cannot really describe during the transport them as their high energy brothers. Like during the transport, you cannot really handle them as particles. Okay. Now, just to avoid confusion, during the transport, we handle like the particle moves from gamma is moving from a point to another point. It doesn't mean that the interactions, like Compton scattering and so on, are described if the gamma would be a particle. Theoretically, the interaction, the differential cross-section, is derived, of course, in such a form that the particle is a wave. Okay, which means that all those cross-sections are coming from quantum mechanical formulation of the scattering and so on. But then we compute the differential cross-section, and after, during the transport, we know the distribution of the energy transfer, for example, because it will be proportional to the differential cross-section. This is what I'm talking when I'm saying that the high energy photons, they are during the tracking, they are handled purely like particle-like. Okay. No, this is not true for the low energy photons, just because their wavelength is so long compared to the interatomic distance already. So whenever we are tracking, there are special effects that coming from this wave-like property, so we need to take into account during their tracking. Very often, energy and momentum is not conserved. It's just because, again, it's yet another things. But you will see examples and you will understand why. And another thing is there are no smooth transition between the optical photon processes to the normal photon interactions. Unfortunately, they are too different. Now, the interactions in which these low energy photons are generated, the Cherenkov effect that I was already mentioned, scintillation and transition radiation. That's actually, scintillation is straightforward. The transition radiation is happening when a charged particle is moving from one material to another, where one material means the material that is described by one dielectric property, and moving to another material that is described by a different dielectrical properties. And the electric field around the charged particle need to adapt to the new dielectric properties, and during this change, there are photon emissions. Okay, these are very low energy photons, and what is in case of Cherenkov, you get many low energy photons. In case of transition radiations, you get many low energy photons. And these low-energy photons are the optical photons. So if you want, these processes are the source of optical photons. Now, what kind of interactions, processes are available, special processes are available for optical photons? There is reflection and reflection at the boundaries, which means when two different materials meet, if you want. Wavelength shifting, bulk absorption, and coherent scattering. We will see briefly each of them in the next slide. In advance, what I was already mentioning is that in order to be able to invoke these processes, the user needs to provide some special additional material properties or some other some photon spectrum or absorption spectrum you will see in order to be able to use these processes. So you need to give a bit of extra already as a user. So let's see these processes one by one. First, the boundary processes. So as you can see, let's move this first. So when the photon reach the boundary of two materials, so some should go through, some should be reflected. Now, this is not possible in Geant4 that you split the particle, okay? So instead, what will happen with some probability, it will be transmitted or reflected. And in order to perform the computation that are necessary for the reflection and the transmission, what you need to there are many information that you need to be available regarding what is the dielectric properties of the two materials at the boundary, one side and on the others, whether it's a dielectric meeting or metal dielectric and so on. Other properties like the properties of the surface is also important in case of these boundary interactions. And the user need to provide this kind of surface properties, for example, in the G4 optical surface model. Now, beyond this boundary interactions that can happen when the optical photon reach the boundary of two different materials, there are other interactions that are described. G4 optical photon wavelength shifting. What is it? Is the possibility that when the photon is propagated in the material, it's absorbed, okay? Then, after a while, with a time delay, another photon with a different wavelength will be emitted. Now, in order to be able to do this interaction, there are three things necessary. Someone needs to tell how far the photon goes till it will be absorbed, which means some absorption length need to be known for this kind of interaction. Second, someone needs to tell what is the delay between the absorption and the emission. And someone needs to tell the spectrum, okay, the wavelength spectrum of the emitted photons. If all these are available, this process can do what is it described. Now, just immediately to confuse, there is an optical absorption process. The difference between this and the previous one, that here the photon is absorbed and absorbed. There is nothing emitted after that, okay? It's the end of the life of this optical photon. And the last interaction is the elastic scattering or coherent scattering of these photons. Just, again, avoiding confusion. This interaction, elastic scattering of photons, also happening not only for optical photons, but for high energy photons, for gamma particles. You will see tomorrow they are in the list of photon interactions, even at high energies. But this description is different compared to that description, because the wavelength is so different that it requires different handling of the interactions. Okay. Now, if we leave behind the optical photons and we move to the last part, as I mentioned before, you, as a user, you need to provide some extra material information already if you want to really simulate optical photons. If you move to phonon or electron hole propagation or channeling, then it's even more interesting. Why? Because there is a general assumption in case of particle transport simulation codes, which means that the material that your detector is composed of is at least polycrystalline, but more often you say that is amorph, which means that there is no any special direction, which means that practically there is no crystalline structure, which means that there is no any special direction in your material. Okay. If it's polycrystalline or amorph, no matter which direction you are looking, the atomic electron density will be the same. Okay. No, this is not true in a crystal, because depending on what is your orientation regarding the crystal, you can see completely different atomic densities. This makes life extremely complicated, and the description of the interactions even more complicated if you want to incorporate crystalline effects. This is why I'm mentioning that in general, usually the electron transport simulation code does not take into account any crystalline effect. We don't talk about cross-section, directional dependent macroscopic cross-section, or directional dependent mean-free path, and so on. Okay. Now, in this case of interactions, when we are talking about electron hole propagation or phonons, phonon does not exist. They need to be crystals. Okay, we will see soon. So even channeling, we cannot talk about channeling if it's not a crystal. So there is an extra information, possibility to provide extra information through this G4 lattice logical regarding the crystal structure. Okay, I will show a link if somebody is interested. What is it? How to use? You can get more details. But what is important is, as I mentioned, that there are no phonons if it's not a crystal, because what are these phonons? Makoto was already showing things on the first yesterday morning. Actually, if you are talking about phonons, you can think about some vibration of the crystals. Okay, you imagine that you have a crystal, the atoms in a nicely ordered way, and somebody, or through some interaction, you move one of the atoms. Now what will happen, other atoms in the neighbor also start to move. And the crystal will start to vibrate. Okay. Now, depending on how the neighboring atoms are moving, if they are in a phase, nicely, like the sound wave is propagating, then you are talking about acoustic phonons. If they are moving into opposite direction, you can talk about optical phonons. This comes from the way of how you can excite such vibrations. But actually, phonons behaves like quasi-particles. They are, from this point of view, similar a bit to some other quasi-particles that also play important role in case of solid-state physics and interactions, actually, called plasmons, which are charge density oscillations. So you can imagine that you have a conductor where you have some free electrons available, and if a charged particle goes through on this free electron gas, if you want, then it will create oscillation of this free electron gas, and which means that it will transfer some energy and momentum to this oscillation. So actually you can handle if it would be a particle, while because the energy, the frequency in which the electron gas will oscillate, it's characteristic to the material. Okay, actually determined by the electronic structure of the solid. So from this point of view, phonons, like plasmons, are some quasi-particles. But also, when this, I describe here this experiment that was motivating this development, and as you can see, the germanium atoms are recoiled, are kicked a bit by some particles that will start to generate this vibration of the crystal, the phonons. And if you are talking about germanium or silicon and so on, you know that in case of semiconductor radiation detector like X-ray detectors, the way in which the radiation is detected is that the photon is absorbed in the detector, and eventually, after many interactions, electron-hole pairs will be created, which means some electrons from the occupied states below the Fermi level will be excited just above in the conduction band to the Fermi level. And there is a field to collect these electron-hole pairs. And if you count them, it will be the number of these electron holes created by a photon will be proportional to the energy of the absorbed photon. Okay, so these electron holes pairs are also created. So since they are created, they need to be transported somehow. And these phonon interactions actually describing how the phonons are transported and what kind of interactions are available. So first of all, they are described like a wave with different with different polarization states, as you can see, and they can have some interactions, some processes, if you want. One is the elastic scattering or isotope scattering, and the second one is this anharmonic down conversation. The phonon scattering, the elastic scattering, is actually, you can imagine when there is this vibration of the crystal, and there is a defect somewhere in the crystal or impurity, then it will disturb this vibration. So this is like if the vibration is propagating, but then there is some kind of kink, if you want, just because of this crystal defect. And what it will cause, it will randomize the polarization state of the phonon, and yes, it will be randomized there. Then the phonon down conversation is actually splitting of the phonon into a longitudinal phonon to the longitudinal transverse or transverse. Okay, not so important. The important things, or at least visible things, is that due to this interaction, due to the elastic scattering, and due to the fact that in a crystal there is a directional dependent elasticity, there will be preferred direction of propagation, depending on the crystal structure, and it results in a nice pattern that called is Phonon Acoustics. And in germanium you can see the simulated image, and you can compare on the right side the experimental image, which is very nice agreement that you can see here. Now I mentioned, phonons, phonon transport, but also created electrons and holes need to be transported. Of course, when they are collected by a field, the electrons will move to one direction, actually jumping from hole to hole, which you see in another way if the holes were moving to another direction. You can see. So this is what's happening in the presence of some electric field. Moreover, when the electrons and holes are moving, they can also excite phonons. Okay, they can make excitation, vibration excitation, and this kind of phonon excitation looks quite similar to the Cherenkov effect. I will show immediately something. So from this point you will see some electrons moving on this direction, and on the same time, as I mentioned, electrons are actually jumping from hole to hole when they are moving. So you see like holes were moving on to the other direction, and when they are moving, they will create phonons that are propagated, and you can see they look really like the Cherenkov radiation, like a shock wave. You can see this red things are the phonons. Finally, it was also mentioned by Makoto, and this also requires knowing the crystal properties and having crystal. If there are no ordering, there is no channeling. So the channeling is that you can, if you put a particle nicely along the planes, the proper planes, that the particle can be trapped in the field. So when you start to bend your crystal, you can drive your particle somewhere, okay, wherever you want. So you can deliver particles into different positions through this nice channeling effect. But of course, again, this effect does not exist if you don't have an ordered atomic structure, which means that if you don't have a crystal material. And you can see that it has been implemented in Geant4. You need to provide, again, some extra information to use these models. But then the measured and the simulated data regarding this channeling are agree very well. Same for the angular deflection. So you could see many kind of exotic physics that do not really fit in the mainstream simulation, but very interesting application and available in a kind of way of extension in Geant4 many times. But most of the time there will be a publication or some description or some description in the documentation together with some examples. So you can go and you can see all the details if you would like to do something similar things. Like in case of phonon propagation, phonon electron hole propagation, or in case of optical photon, you can find the detailed documentation at this point. Any questions? So the nap is over because it's geometry, I think, and it's much more important for the application.
Thank you. Okay, so this is Geometry 2 talk. So it continues how you describe geometry. Now, after this particular talk, you should be able to describe much more complicated geometry. Okay. Oops. No, it's okay. Okay. Yes. Yes. So it has just basically two big topics. One is various ways of placement. Okay, how to locate volumes. Okay, and it's just a small addition of what's called touchable. Okay, but as you see, there are a lot of different ways to specify the position of volumes. Not only one volume, but volumes. But I have to start from this one again. So in this particular talk, we stick on to this part only. Okay? We have already discussed about the solid. We have already discussed about the logical volume. That part is already done. Okay? Just only for the physical volume. And in my previous talk, we just stick on to this PV placement, the simplest one. Okay? So we have a lot of other different ways. Okay? So we have already discussed about displacement volume. It is one position volume. So in this case, you have just one chair at a time. Okay? In your memory, if you want to have 100 chairs, each chair has its own object in the memory, representing individual one chair, okay? And it knows where it is, maybe with rotation, okay? But repeated volume is a completely different way of defining things. Make each physical volume object in the memory intelligent, so that by asking the copy number, it returns different, let's say, position. Okay? So you need only one object with a lot of code, not necessarily a lot, but some implementations. Okay? So it's not a simple data object, but with some programs, it returns the position depending upon copy number, for example. Okay? So that is what we call repeated volumes. So one object in the memory represents any number of the real volumes. So if we implement these chairs in this way, in the memory, there will be only one object in the memory that represents all of these 100 chairs. Okay? So it significantly reduces the size of memory. And there are several different ways. The first one is parameterized volume. You may realize that we are international collaborations, so we don't have any strict rules of the spelling rule. So this is British spelling. But if you see all the Geant4 implementations, there are 4 different spelling of parameterized. One is S, one is Z, parameterized, yeah, arbitrary. There's no strict rule. So we are so sorry, but you really have to look into our code to see which spelling we use for that particular class. Okay, depending upon who implemented that class, spelling is different. Okay, and replica and division. There are simple repetition along one axis. But anyway, so there are many different ways. So please note, the mother volume can contain either many placement volumes or just one repeated volume. You cannot mix them up. Once you decide to implement all these 100 chairs with placement volume, okay, you have to finish it up with placement. So you really have to have 100 objects. Once you decide to use parameterized volume, you have to implement the parameterization that can take care of 100 chairs. You cannot say, okay, I implement 50 chairs one by one and take care of another 50 chairs by parameterized volume. You cannot. Okay? One or the other. So now let's go one by one. So placement we have already discussed. Placement is one placement volume. Okay. So next one is G4PV parameterized. That is the parameterization. The thing is parameterized by copy number. So you can parameterize not only the position, rotation, but shape, size, material, sensitivity, a lot of things. I'll discuss in detail of this later. Because you can parameterize basically anything. You have to implement your own implementation. This should read D4V. That V is virtual. Physical volume parameterization. Okay, stupid wrong name. But anyway, that is the base class. You have to create your own parameterization class derived from this guy. Okay. And as an extension of this PV parameterized, we also have G4PV nested parameterization. Okay, this is absolutely useful, in particular for medical users. Actually, how many of you are medical users? One? Just one? Okay. And sorry, how many of you are high energy physics? Okay, half of you. And nuclear physics? Okay, duplicated, yes. And then space? Okay. And then what else? Security, maybe? Yeah, security or industry people usually don't raise their hands, I know. They are secret, yes. Secret agent. Anyway, so in particular, this is medical. But I come back to this later within this talk. Now, physical volume replica. It's a simple repetition. Or you can take it as a slicing. One motherboard box into the pieces by slicing. Okay? And division is also slicing, but with some gap. And reflection factory is useful only for high energy physics, I believe. It's a mirror reflection of one side from the other in a collider detector. Okay? And assembly volume. And this is a kind of interesting concept of grouping the volumes and place the group. Okay, so I will go one after the other. Okay. So, parameterized volume. This is a constructor, G4PV parameterized. Please, this is a kind of physical volume. So the base class of this constructor pointer is G4V physical volume. Okay, it takes name, it takes logical volume of itself, it takes logical volume of mother, and here's the axis. I come back to this later. But it basically says along which direction, X, Y, or Z, in particular which axis the repetition dominates. It's a suggestion. I'll come back to this later when I tell you how we optimize the geometry. Okay? Then here, number of replicas. If we implement this classroom, we have to say 100 because we have 100 chairs. Okay? Then this is the guy, this is the class you have to implement, parameterization. Okay? Okay? So it replicates the volumes n replicas times using the parameterization you specify, this is P param, okay, within the mother volume. Okay? So as I said, P-axis here is a suggestion to the navigator along which Cartesian axis repetition dominates. Okay? X, Y, or Z, and if it's really random, you can say undefined. Okay? but you have to pay a penalty, and that's something I'm going to discuss later. So, parameterized volume. So you have to implement parameterization, okay, by yourself, and define position or rotation or whatever as a function of the copy number, okay. So the parameterization could be where it is positioned in transformation rotation as a function of copy number, like this. Copy number 0, 1, 2, they are the same kind of box, but in a different location. So with this particular parameterized volume, if navigator asks where the volume is, with copy number 0, it says I'm here. With copy number 1, it says I'm there, different position. Okay. So in this classroom, if navigator asks copy number 0 of the chair, it said there. Okay. Then if copy number 1 is the next, and so on and so forth, up to copy number 100 over there. Okay. And optionally, the size of the solid dimension. So copy number 3 could be larger. Okay. And type of the solid, material sensitivity, and so on and so forth. So 4 could be made of different size, but also different material. Another different material, different shape, size, and even different solid, In this case, it's a cylinder. Okay? Yeah, because if you really want to implement this classroom, in addition to the 100 chairs, we have tables. Okay? And as I said, you cannot mix placement and parameterized volume. Okay? Given there are only 2-3 tables, it's easier if you implement, these tables by placement, while you implement 100 chairs by parameterized. But I'm sorry, but we cannot do that. Once you start implementing parameterized volume, you have to finish with parameterized volume. So copy number 101 could be that table. Okay? That means you have to change the shape and material as well. Okay. Of course, all daughters must be fully contained in the mother. Chair, copy number 95, whatever, cannot be outside of this classroom. No. Okay. Everything has to be inside. Okay. And daughters, each other, should not overlap. Okay. There cannot be any, physically impossible if 2 chairs are overlapping to each other. And if this happens, Geant4 navigation will be totally screwed up. There's whatever, nothing could happen. Okay, I'll discuss it later. So it applies to only the simple CSD solid only. You cannot use it in Boolean. You cannot use it for tessellated solid. Okay. Granddaughter volume is allowed only for the special cases. That is, given you can change the size of the volumes, but still they all share the same logical volume. Okay? And mother-daughter relationship is an attribute of logical volume. We're just changing the size dynamically. So if any daughters fits into this volume, number 3, it does not guarantee if it fits to the other shape. Okay, that's the reason why you can place granddaughter volumes only if you are not changing shape or size. Okay. So, typical use cases is for example, in a calorimeter, if there are a lot of cells, it's very easy to use this. Okay? And for the medical applications, if you have CT scan data, each box cell is a box. The only difference is the material and its position. Okay? The size is always the same. It's very easy use case for the parameterized volume. Okay? any quick question for this parameterized volume? Of course, I have a few more slides, but.
Yeah. So let's say that by mistake I overlap some daughters by mistake. So in this case, I'll get some warning through that parameter.
Be patient. In my geometry 3 presentation, there are a lot of discussion there.
Okay.
Yes. And most of the, in short, no. If you are lucky, yes. So here's some cheap example. Here's a solid of whatever the size. And please, even if you are changing the shape or changing the size, we still need a default. So take whatever the typical shape and typical size. Then it's a logical volume. Again, as I said, you may even parameterize materials. But even if you parameterize the material, we still need a default. So whatever the material is okay, but set it. Okay. Then this is your class, chamber parameterization. That's something you implement. It's a parameterization. Instantiate and give it to the PB parameterized. Okay, here, parameterization. And this is the number of the objects, number of the daughter volumes in this model. Okay. In this classroom, we have 100 chairs, 3 tables. Okay, so that should be 103. Okay. And in this case, if I may say this is y, let's say this is y-axis, so this should be not z but y, because this in this way they're the biggest repetitions. Okay. And here is the parameterization. This is something you have to implement. Okay. First is compute transformation. You get the copy number, and you calculate the position rotation for each individual copy number. Okay. Here the compute dimensions, you change the size. Here compute solid, you change the shape. Compute material, here you parameterize the material. And also, if you like, you can also parameterize color, sensitivity, and a lot of other things. Okay. Got it? Now, let's go to the inside of each method. Here, the compute transformation. You get the copy number and physical volume. Okay? It's the base class. So you calculate position with respect to the copy number. You calculate rotation if you need it, and so on and so forth, and set translation and set rotation. Okay. And to implement this class, please, if you need sine, cosine, exponential, not realistic, but that you may find sine, cosine quite often. Okay, don't calculate it, because this method is invoked in the tracking time with every step. So if you recalculate cosine 10 degree for every step, it just simply destroys the performance. If you need to have such numbers, please pre-calculate when you instantiate this class itself. In the constructor, you should have all the deep calculations, all the heavy calculations. Okay. The second is compute dimensions. In this case, if you look into the base class, it takes with the same method name, but there are quite a many methods defined. The difference is the type of the shape. Okay. So it's really for each shape you use, you have to implement this method, because the number of the parameters you need for the size to describe the size depending upon the shape. So we really have to have shapes, methods that represent each individual shape. Okay. So this is the box simplest one. You get the copy number. So basically you just calculate the size and set the size of of this particular box, okay, as a function of copy number. Okay. Then next, the compute solid. You get copy number. So if copy number is 0, it's a box. If copy number is 1, it's a tube, and so on and so forth. In this case, please do not instantiate solid here. You have to instantiate solid when you construct the object. Otherwise, for every step you create a new solid. If you have million steps, you end up with million solids. It's wrong. Okay? And depending upon the copy number, you return the solid. Got it? Now the last one, on the compute material. You get the copy number and the physical volume and touchable. That is something I'm going to discuss very soon. Okay? And based on the copy number, you say if copy number is 0, it is made of water. If copy number is 1, it is made of air or lead or whatever. Okay? That's it. In this case, please do not instantiate material here. The same story. If you have a million steps, you end up with million duplication of the material object. No. So it has to be already defined. Okay? And in addition, the material has to be returned, but also you can get the logical volume. So you can set visualization attribute, for example, if you like, to change the color depending upon the copy number, or sensitivity. Okay? You can do a lot of things. Basically, almost all the attributes you may set to the logical volume. You can change it here. Okay. Any question? Yeah, it looks like complicated. I know. But even this afternoon, you try it, and you see. Okay? Because if you have already tried B5, basic 5 example, you have already seen some crystals, calorimeters. That was parameterized volume. Okay, we implement it. Okay, today. Now, replicated volume. In this case, the mother volume is completely filled with replicas, daughters. All of these replicas are exactly the same size and shape. So, suppose this is the mother volume and this is the daughter, like this. You fill up the mother with the daughters. No gap anywhere. Okay? It means you have a cake, you slice it. That's it. Okay? So the replication may occur along one of the Cartesian axes, x, y, z, okay, or radial in a row, or phi. Okay. So here's the replica constructor. Again, this is a kind of physical volume. Okay. So it takes a name, logical volume of the mother. In this case, it's not a suggestion, but it's a linear order in which axis you want to make a slice. Okay? And number of piece replicas, and width and offset, I'll come back to this very soon. Okay? And replicas can be placed inside other replicas because we can guarantee all of the pieces are the same shape and same size. Okay? So if you have a big box, you may start slicing it in x-axis. You have a plate. Then for this plate, you may slice this second direction y. You have a big long rod. Okay? Then slice it in z-axis. Then you have a small box. Okay? Got it? You can slice only one direction at a time, but you can do it sequentially to make it smaller piece, create a smaller piece. Okay. So for example, for the case of Cartesian axis x, y, or z, here's the slice. And in the case of radial slice, starting from the innermost to the outermost, this is the slice. But only for this particular case, we cannot expect you to do any data inside, because it's quite obvious that this one, the innermost part and the other outer part, the size is different. Okay, shape is different. So you cannot say any volume is here inside this red ribbon. Okay, because if for the next slice, it's outside. So you cannot really put anything inside. So if you want to slice a tube, you should always start with Z. Then you have a disk. Then start the cut in phi. You have this. Okay. Then you start slicing in row. Then you're okay. Okay. If you do other order, it doesn't work. Okay. So here's a small example. Here's a donut. Okay. Unfortunately, you have only donut to be eaten by 6 people, so you have to cut it in 6. Okay. Yes. So first is the full pi, full coverage, so that it's 2 pi radian. So here's a tube. Inner radius is 20 centimeter, outer is 50, and height is 60. Because this is half height. Okay. Start angle is 0 and 2 pi, so it's really a full ring. Okay. It's made of something, let's say air, and now it's physical volume. It's placed somewhere, so it's a real, thing. Now we have this angle that is 1/6 of the full 360 degrees, so it's 60 degrees, And here is the solid. So it's starting from minus 30 degrees to plus 30 degrees with the same size, same inner radius, outer radius, and half height. So this is here. Okay. Then logical volume. You take this solid, and it's made of lead rather than air. Okay. Now you say replica in 5 direction with 6 pieces. Okay, and this is the span. That makes 6 pieces. Okay. At this guy, this is only one object in the memory. That represents 6 pieces. Okay. And if you ask copy number 0, it says I'm here. But if you ask the same guy, where are you? With copy number 1, it says I'm here. So on and so forth. In this case, it's simple slice, so that you don't have to implement any parameterization, complicated parameterization. We know what you want. So that's it. And if your repetition is this simple, please always use replica rather than parameterized volume, because the logic itself is much simpler and faster. It's guaranteed it's faster. Okay? And it's guaranteed there cannot be any overlap, because we take care of it correctly. Okay? Now, divided volume. It's very similar to replica. The only difference is the following. You fill daughters of the same size and same shape, but some gap here. That is the only difference. At the beginning and the end, there could be a gap. That's it. So there are 3 constructors. One of them is here. It takes axis, number of divisions, and offset. Offset is here. If you use this one, we place daughters like this. Okay? Because we can calculate the actual size And you provide division, so we can really calculate the width of daughters. Okay. The second one, it takes axis, width, and offset. In this case, we put daughters as many times as we can. And if the remaining is smaller than the width, we can't put it. Okay, that's it. The third one is the mixture of these. Axis, number of divisions, width, on offset. In this case, we just put as many as you requested. In this case, the gap remaining here could be larger than the width. Okay, that's it. And you may say this is not very useful because there is no gap allowed. Yes, true. So, but anyway, we have divisions for a lot of different shapes. And in addition, as an extension of divisions, we have replicated slice. The difference is for each of these three constructors, you can say one more parameter. That is the gap, half gap between the slices. So, as you see, we place like this. Then put real daughters with gap. So as you see, you may have gaps. So it's really exactly the same style like previous, but in this case you have gaps. This is more realistic situations. Okay. And in this case, if you, for example, specify the material of the mother volume is made of air, and material of this daughter is made of, say, lead, then this gap is filled by air because it does not belong to the daughter. Okay? So, for example, if you have lead scintillator sandwich calorimeters, make the big lead box, use replica with gaps for the scintillators. Then you can easily have the sandwich calorimeter very easily. Okay, and so the half width is the half thickness of the lead absorber, right? So it's very useful, and this is reasonably powerful. Oops. Please. Any question here? Okay, next is nested parameterization for medical, but may also be also useful for space and also material science as well. Anyway, let's see. So, suppose your geometry is three-dimensional regular repetition of same shape. This is typically the case of the CT scan data. That the format is DICOM. Okay. You know what CT scan is. So it's really a box, many number of boxes, exactly the same size, typically 1 millimeter cube or 2. Okay, and each box cell has different material. Here's my fat, here's my muscle, very poor, or liver or lung or whatever. Okay, so for each box cell has its own material, but the size is exactly the same. And the position is changing each other, touching to each other. There is no gap between. Okay, so we can already implement it by parameterized volume, like this. Oops, please. In this case, just 36 cells, and just for explanation purposes. There are gaps, but in reality, they are touching to each other, of course. Okay? So, in this case, you have to implement your own parameterization class, starting from copy number 0 to 35, in total of 36 box cells. For each box cell, you say, here's material of fat, muscle, bone, liver, whatever. Okay? That way. You can do that already. But there is another and better way to implement it. Because this three-dimensional parameterization, navigation is quite costly and slow. And also it requires quite a bit of memory. So instead, we can do the following. First, we use replica to slice in one direction. Then take just one piece to make another slice by replica. Then take another piece, only one piece here. And in this case, we use parameterized volume, parameterized only in one particular axis. In this way, navigator is ultra faster compared to that one. Because in this case, we have to think about three-dimensional navigation. Here, we already know first and second dimension is replica. That is ultra faster. And also, the third dimension, it's parameterized volume, but still, we know it just simply aligned along the third axis. So it's much faster. But the problem is the following. If we use the naive parameterization, you can change the material by the copy number. Yes, but you have only 4 volumes here. Okay? Copy number 0, 1, 2, 3, that's it. You cannot represent 36 different materials. So we need this nested parameterization. It's basically the same as parameterized ordinary parameterization. Sorry, let me start from here. Copy number 0, 1, 2. Then the second axis copy number 0, 1, 2. And third axis copy number 0, 1, 2, 3. Okay? So all the difference is, for the case of nested parameterization, you need not only the copy number of itself, 0, 1, 2, 3. You need 2 more copy numbers of its mother and grandmother. By 3 indices, you can say, yes, it's a liver, or it's a muscle, or it's a fat. Okay? So that is the only difference. So here we have touchable. Touchable is something I'm going to discuss later. Okay? But it remembers the copy number of all the geometrical hierarchies. Okay? So the third index is a copy number of itself, 0, 1, 2, 3. Okay? Then in the second axis, 0, 1, 2 could be given here by asking touchable and get copy number of 0th order. Here, the one level up. So the first axis, you can still ask a touchable to get copy number of the level one level up. Okay? So you get IX, IY, and IZ, let's say, 3 indices. By these 3 indices, you can calculate, or you can look up to the map, what is this particular material of this cell. Got it? So the only difference is, instead of parameterizing material in one index, you have 3 indices. That's it. Okay? But to get these parents indices or ancestor indices, we need to introduce the touchable. So for the case of nested parameterization, it's derived from the ordinary G4V physical volume parameterization. Sorry, I misspelled here. This should be S. Yeah. So it had 3 pure virtual methods you really have to implement. Okay. Also, in addition to the compute transformation method. Okay. So first with compute material. Here you get the current volume, copy number, and touchable for the parent. Okay. Return the material pointer with respect to the copy numbers of itself and ancestors, mother and grandmother. Okay. And please, you must cope with the touchable pointer, null pointer, for navigator's sake, because at the initialization time, we invoke this method once, and with null pointer. So if your code is not well protected, you got a crash. Okay? So if this touchable is null, you may pick whatever the random material you want and just return it, please. We don't use it, but at least it has to run. Okay? So please, the first line of your implementation should be check if this touchable is null. If it is null, return the first material you may want to use. Okay. The second method is now get number of materials. We invoke this method when we start to calculate cross-section tables. So you have to say, in our nested parameterization, we are going to use 5 different materials in total. Then you say 5. Then we invoke this get material method with all the indexes, in material indexes you use, material number 0, 1, 2, 3, 4, all 5 materials to calculate the cross-section tables for each material. Okay? We need this because even if you have millions of voxels in CT scan data, you don't have million different materials. There are only 10, 15 different materials, okay, for different organs. That's the reason why we cannot easily predict how many different materials you may employ. Okay, so that we have to have these material and these two methods. Okay. Questions? Okay, now assembly volume. Here, like this. If there are quite dense, complicated geometry, but with some patterns of repetitions, actually, you can imagine how I could draw this picture, in PowerPoint. I started to draw these 3, and I grouped it and made a copy. And then for each copy, I slightly turned it. Okay? So this assembly volume or grouping, it does exactly the same. Okay? First, you group these 3 and make imprint. That's it. So here the assembly volume. So I think it's better going this way. Okay. So you instantiate just empty assembly volume. So it does not have any boundary because you are just going to create a group, right? But it still has the coordinate system. Center is the origin, X, Y, Z axis, so that you have one logical address volume. This is one volume with this translation and rotation. Okay. So you define it with respect to this virtual coordinate system of the. Okay. Then you repeat whatever the number of daughters you need. Okay. Then here's the loop, make imprint. And in this case, this rotation and transformation is with respect to the mother volume, you say the center of this assembly volume, where it should be. Okay? Then we create this imprint, and so on and so forth. Okay, this way. And given assembly volume does not have any shape, there is no overlap here. Okay? If you just define whatever the real mother volume, you cannot copy them because mother volumes are overlapping to each other. So this is the way, if you have silicon microstrip detector kind of things, this is the only way you can implement easily. Okay? Otherwise, of course, you can do all 12 things one after the other, but it's not nice. So we offer this functionality. Now, reflected S. Sorry, I cannot hear. Yes, it's okay. That's just to make sure you have no real overlap. Yes. Yeah, so he said, in this case, I just rotate this way, but if you need, you can rotate the other way as well. But just to make sure there is no real overlap. Assembly volume itself may overlap because there is nothing here. It's a virtual concept. But once you make an imprint, these are real placement volumes. So that they should not overlap to each other. And that is user's responsibility. Okay. Now, reflected volume. It makes sense only for the collider detector. Okay. And, inside is always an electromagnetic calorimeter followed by hadronic calorimeter. And segmentation is, if this is clockwise, the other side is counterclockwise. It has to be. Okay? But because of this, such geometry cannot be made by parallel transformation. If you just move it to the other side, it's inside out. It's wrong. Okay? Or rotations. Because once you rotate it, the other side is also clockwise. It's wrong. So if you have, clockwise this side, the other side has to be counterclockwise. So neither linear transfer or rotation doesn't work. Okay? So we have deflection factory. Let me skip all the details, but what it does is first you implement all the geometry of one side, ask the reflection factory to create its reflection. Then for each volume, it's a left-handed system, and the reflection factory creates its mirror symmetric one, that is left-handed. Okay, so just once create one side, and ask reflection factory to create the other side. That's it. Okay. But there are some small blah blahs, but it's okay. So I have to go to touchable. Yes. This is quite important concept you have to understand. Okay. When you use any repeated volume. Okay. So this is not geometry, but how you access to the geometry. Okay? As mentioned already, G4 step has two G4 step point objects that represent starting and ending point of each step. You remember, right? And all the geometrical information of the particular step should be asked from the pre-step point, because, as you know, if the step is limited by the volume boundary, it physically stands on the boundary, but it logically belongs to the next volume. Okay? And so let's start with this example. It's a very simple two-dimensional array of calorimeter or something. For visualization purposes, there are gaps, but in reality, these gray boxes are touching to each other without any gap, because it's a calorimeter. Okay? So how do you implement it? You start with a big box, then, copy replica in one direction, followed by other replica in the second direction. Okay? But, but this is good. Please, how many objects in the memory do you have? For purple one, big one, yes, there's one object. And once you make a slice of this blue, there's only one replica object in the memory. Okay? That represents all these four layers. And there's only one gray object in the memory that represents all these 5 cells. Suppose particle goes from here, ended up with this boundary. It physically stands on the boundary, but logically belongs to the next volume. And once this step is already made, objects in the memory is already updated. So if you ask to the volume itself, what is the copy number? It replies 2. Okay? But as you see, this step belongs to copy number 1. If you ask to the physical volume of the copy number, you get the wrong number. Okay? So for the case of this one, it comes down from here to there. So this is the end point. It belongs to this guy. In this case, you are okay. Both are the 3. But if you ask to the copy number of the mother, it's wrong. Because there's only one object of this cyan or blue, whatever you call, object in the memory. The data of the copy number is already updated. So you have completely lost already to know which was really the copy number of the volume that step belongs to. Because that can be from this side. So there's no way you can tell. Okay? But instead, we have already made a copy of this information into a touchable. Okay? As I said, touchable remembers all the copy numbers of all the hierarchies. Not only the copy number, but also transformation. So, you should not ask the information of the track, but you always have to go to the touchable. For each step point has its own touchable. It remembers all the necessary geometry information where it started. Okay? So, touchable. You get a step. You get the pre-step point by asking get pre-step point. It's a step point. Then you get a touchable asking to the pre-step point. The copy number, just ask copy number. If you need the copy number of mother, just one level up. 2 level up, you get the copy number of the grandmother. Okay? It is, in this case, it is guaranteed because it is saved in the memory that before we really push the particle. So it really remembers all the copy numbers of the hierarchy. And also, position in the world coordinate system is, you can take it to the point. As I said in my first talk, the position is always given in the world coordinate system. But you need to transform it to the local coordinate system if you have, for example, drift chamber or any position sensitive detector. Okay? In this case, this touchable has a transformation. So just provide world coordinate system position and use this transform method, you get the local point. Okay? It's also guaranteed it works. Okay? So when you need to access to the volume information, geometry information, whenever you need, you should always go through pre-step point, please. Okay? If you look into the LXR code browser for G4 track, it also has get volume. But this is for physics. It's not for the user. Because once particle is already moved, it returns the post-step point information. It's already wrong. So please, you should always go to pre-step point. Okay? Untouchable gives you all the geometrical information. Got it? This is essential when you need to extract any information. Okay? For example, if you need to accumulate energy deposition, don't get the wrong copy number of the cell. It's wrong. Okay. Okay, that's it. Question? And you'll see it. It looks like complicated, but once you try it out, it's not that complicated. Okay? But this is essential. And don't ask me the meaning of touchable. It's not in my dictionary, although the concept was invented by me. Okay. Then go to the tutorial.